Yes, please. Now start writing again. OP of the solution is directly proportional to molarity of the solution and temperature. Now copy from the board. Symbol for osmotic pressure is pi. So pi directly proportional to molarity and directly proportional to temperature. Or I can say pi is directly proportional to m into T. Or I can say pi is equal to R is constant, R is gas constant, R into MT, or I can say pi is equal to MRT. This first equation of fourth colligative property, that's why I've numbered it as 4A. Now, why have we used molarity in this case? We have been using molality in elevation and boiling point and depression and freezing point. Why have we used molality in this case? Remember, when we perform the experiment on elevation and boiling point, we have to heat. When we perform the experiment on depression and freezing point, we have to cool the solution. It means change in temperature is involved. And with change in temperature, molarity changes, but molality does not change. But in case of osmotic pressure, we can perform the experiment of osmotic pressure at any fixed temperature. No change in temperature is required. And this is the reason molarity is used in the calculation of osmotic pressure. Right on. Since OP is determined at a fixed temperature, molarity of solution does not change. That is why molarity is used in the calculation of OP, is used in the calculation of osmotic pressure. Next paragraph. Equation 4A can be modified. Equation 4A can be modified as follows. I'm modifying this equation. Sorry, this is pi. Pi is equal to, molarity is number of moles of solute per liter of solution. So this I'm writing as NB divided by V into RT, or I can say pi V is equal to NB RT. This is the second equation of fourth colligative property. Pi, pi is osmotic pressure. Units of pi will be atm, atmosphere, or bar. NB, number of moles of solute. This I need not tell. This is volume of solution. And this volume of solution should be in liters. R is gas constant. Whatever is the unit of R, same will be the unit of pi. We can use 0.0821 liter atmosphere per Kelvin per mole. If we use this value, then pi will be on atmosphere scale. Or I can use 0.083 liter bar per Kelvin per mole. If I use the second value, then units of pi will be on bar scale. I've shared one numerical. Check your WhatsApp. Sharing in the chat box also. Numericals are generally simple on osmotic pressure. Yes. Numerical is calculate OP of the solution at 27 degrees centigrade, 10 liters of which contains 18 grams of solute, molecular weight is 90. Pi is pi into V, 10 liters of solution. Number of moles will be 18 grams, molecular weight is 90. 18 divided by 90, 0.0821, and temperature on Kelvin scale will be 300. So answer will be 0.4926 atmosphere. 0.4926 atmosphere will be the value of osmotic pressure. Further write down. If the solution contains two or more non-volatile solutes, then equation 4b becomes now how do we modify equation 4b? This is number of moles of solute. Now in place of number of moles of solute, we'll use sum of the number of moles of different solutes. So equation becomes pi b is equal to NB1 plus NB2 plus so on. This is sum of the number of moles of non-volatile solutes into RT. This is equation number 4C. Yes, one thing more, I forgot to tell you that equation number 4B, that 4B is called Van Hoff's equation. Equation 4B is called Van Hoff's equation. Now again, one numerical on 4C. Yes, I've shared. Check it. Numerical is 1.6 liters of a solution contains 12 grams of urea and 18 grams of glucose. Calculate OP at 47 degrees centigrade. Pi we have to calculate. Volume is 1.6 liters. Number of moles of both the solutes will be added. One solute is 12 grams of urea, 12 by 60. Second solute is 18 grams of glucose, 18 divided by 180 into R into temperature. 47 will be 350 Kelvin. This will give you the answer. This will be 4.926 atmosphere. 4.926 atmosphere. Now look here. Let us say this is a vessel. In the middle of the vessel is a semi-permeable membrane. On one side of this semi-permeable membrane is a concentrated solution. On the other side of SPM is a dilute solution. Osmosis will take place. Solvent will flow from dilute solution towards concentrated solution. Now, in such cases, how much will be the osmotic pressure generated? How do we calculate? It's a very, very simple equation. Right on. If two solutions are separated from each other through a semi-permeable membrane, then OP generated can be calculated by using the equation can be calculated by using the equation pi is equal to m1 m2 minus m1 into RT. Out of two solutions, that solution whose molarity is higher, that is M2, and the other one is M1. Now we'll use this equation and calculate one numerical. Yes, this one. 0.9 molar solution of urea and 1.2 molar solution of glucose are separate from each other by through SPM at 27 degrees centigrade. Calculate OP generated. Higher molarity is 1.2, lower molarity is 0.9 into R into T. 27 means 300 Kelvin. As simple as this. Very simple. So this will be 7.389 atmosphere. Now, in this topic of osmotic pressure, there are many small topics and they're all very important theoretical topics. Pattern, next paragraph. See, plants absorb water and minerals from soil. How do these minerals and water go to top of the tree? That is by the process of osmosis. Just write one sentence. Movement of water from soil into plants through roots is partly due to osmosis. Now we are coming to very important topics on osmotic pressure. See, all the four colligative properties can be used to determine molecular weight of solute. If you look at these, if you analyze all these equations of four colligative properties, you'll find that any colligative property is inversely proportional to molecular weight of the solute. Although any one of these properties can be used to find out molecular weight of solute, but if we want to determine molecular weight of proteins and enzymes, particularly enzymes, are sensitive to temperature and pH. So if we want to determine molecular weight of enzymes, then osmotic pressure is considered as the best colligative property. Why it is so? There are two reasons behind it. First, you write one sentence, then I'll explain one reason at a time and then dictate you. These are very simple and very important reason frequently asked in the exam. That OP is considered as the best colligative property, best CP, to determine molecular weight of proteins and enzymes due to following reasons. Number one. Now let me explain. See, when you perform experiment in physics, I think you calculate percentage error also, experimental error. If you want to determine the value, if you want to find out a value experimentally, whose value you expect to be very small, then slight experimental error in its determination will be a high percentage error. I'll repeat. If the value is very small and there is some experiment, slight error in the experiment to determine that value, for the determination of that small value, experimental error becomes a high percentage error. Remember, values of elevation in boiling point, depression in freezing point, and relative lowering of vapor pressure. Values of these three colligative properties are very small. Therefore, if there is slight error in their determination, that will lead to high percentage error in the calculated molecular weight. But value of osmotic pressure is generally high. Therefore, when we determine osmotic pressure, slight error in this case will be a negligible error. So write on number one, first reason, values of relative lowering of VP, relative lowering of vapor pressure, comma delta TB and delta TF are very small. Therefore, slight error in their determination, leads to a high percentage error in the calculated molecular weight. High percentage error in the calculated molecular weight. Second reason, you might have heard of denaturation of proteins and enzymes. These compounds, proteins and enzymes, they are stable at body temperature and body pH. Particularly, we're talking about enzymes. If we perform the experiment on elevation or depression, temperature will be either very high or very low. At these high or low temperatures, enzymes will undergo denaturation, right? Their structure will change. They will lose their biological activity as well. On the other hand, experiment on osmotic pressure can be performed at any temperature. Let us say I take out an enzyme from my body. I want to find out its molecular weight. I'll perform the experiment of osmotic pressure at my body temperature. Since temperature has not been changed, enzyme will not get denatured. So this is the second reason. Right on number two, enzymes are stable. Enzymes are stable at a narrow temperature and pH range. At a narrow temperature and pH range of the body. Full stop. Delta TB and delta TF are determined at very high and very low temperatures at which enzymes get denatured. However, OP can be determined at any suitable temperature without any denaturation. Next topic. Isotonic or isosmotic solutions. This word is combination of two words, iso plus osmotic, becomes isosmotic. Iso means same, osmotic means osmotic pressure. It means those solutions which exert same osmotic pressure, they are called isotonic or isosmotic solutions. Pattern are those which exert same OP at the same temperature. When two isotonic solutions are separated by a SPM in the middle, and these two solutions on either side by a SPM, osmosis does not take place. Right? So since osmotic pressure is same, osmosis will not take place if they are separated by semi-permeable membrane. Cell fluid. Inside the living cell, there is a liquid called cell fluid. Cell fluid and 0.91% NaCl solution are isotonic. Right? Cell fluid and 0.91% solution of sodium chloride in water, they have same osmotic pressure. That is why 0.91% NaCl solution is called normal saline solution. Normal saline solution. Next topic. Hypotonic solutions. Hypotonic solutions. One topic is hypotonic, the other will be hypertonic. That will be opposite to this. Let me explain quickly. Hypotonic solution is that whose osmotic pressure is lower than the osmotic pressure of cell fluid. Whose osmotic pressure is lower than the osmotic pressure of cell fluid. Let us say in a beaker, in a vessel, we have hypotonic solution and we keep a living cell in it. Cell wall behaves as a semi-permeable membrane. Outside is hypotonic solution. Inside is cell fluid. Now, osmosis will take place and solvent will enter the cell because inside the solution is more concentrated than the solution outside. When solvent flows inside a closed vessel, osmosis is called endosmosis. So we can say due to endosmosis, solvent will enter inside the cell and the cell will gradually swell up. Due to this, some pressure will be developed inside the cell and this pressure is called turgor. In case this turgor is high, then it may lead to bursting of the cell. And if the cell bursts, it is called hemolysis of the cell. Now, patients are given injection, intravenous injection. In this intravenous injection, medicine is not dissolved in pure water. Because if medicine is dissolved in pure water to prepare that injection, that solution of medicine will be a hypotonic solution, which will lead to hemolysis, that is bursting of the cell, as I explained. Rather, medicine is dissolved in saline water so that osmotic pressure of the injection, the medicine, is same as the osmotic pressure of cell fluid, so that bursting of the cell does not take place. Now write down. Hypotonic solutions are those which exert lower OP, lower osmotic pressure than the OP of cell fluid. Cell fluid. If a living cell is placed in a hypotonic solution, end osmosis takes place. That is, water enters inside the cell and it swells up. Pressure developed inside the cell due to end osmosis is called turgor. If turgor leads to bursting of the cell, it is called hemolysis. That is why to prepare intravenous injections, medicine is dissolved in saline water, which is isotonic with cell fluid. If medicine is dissolved in pure water, solution will be hypotonic, which will lead to bursting of some cells. Next topic. Hypertonic solutions. Hypertonic. As I told you, this will be opposite to hypotonic. It means hypertonic solution is that whose osmotic pressure is more than the osmotic pressure of cell fluid. If we keep a living cell in a hypertonic solution, osmosis will take place in this direction. Means water will flow out of the cell, and this flow of solvent outside a closed vessel is called exosmosis. What will happen? Due to this, cell will shrink. And this shrinking of the cell is called plasmolysis. Also called crenation. This is called plasmolysis, also called crenation. Let me explain everything, then I'll dictate. I hope you know meat is preserved by applying salt. Meat is preserved by applying salt, and fruits can be preserved for a little longer time by applying sugar solution. Why? Meat and sugar solution will form a hypertonic solution on the surface of meat or vegetable or fruit. Bacteria present in this solution will lose water by exosmosis and they will die. That's how vegetables and meat are preserved. One thing more, if you remember, I told you about one disease called anoxia in Henry's law. I'm going to tell you one more disease. Now, there are some people who take a lot of salt, high concentration of salt. And those who take high concentration of salt, they suffer from the disease called edema. Edema. Now, what is edema? Edema is accumulation of water in different parts of the body. Why does this accumulation of water takes place? Because water comes out from cells by exosmosis, and sometimes it accumulates in different parts of the body, leading to swelling, and that is called edema. So I've covered everything. I'll dictate in hypertonic solutions. Pattern heading: hypertonic solutions are those which exert higher OP than the OP of cell fluid. If a living cell is placed in a hypertonic solution, exosmosis takes place. That is, water flows out of the cell. Due to this, cell shrinks, which is called plasmolysis or crenation. Plasmolysis or crenation. Next paragraph. People taking lot of salt suffer from swelling called edema. EDEMA, called edema. This happens due to retention of water in intercellular space in between cells, in intercellular spaces by exosmosis. Again, next paragraph. Meat is preserved by applying salt, and fruits by applying sugar, because salt and sugar form hypertonic solution, so that bacteria present on meat and fruits lose water by exosmosis and die. Generally, from osmotic pressure, many theoretical questions are asked. Now, again, I'm going to explain you something. Listen carefully. Most of you take egg. If you peel a boiled egg, you might have noticed that immediately under that hard shell of the egg, there is a very thin membrane. Naturally, this thin membrane is present even if the egg is not boiled. And this thin membrane, which I'm talking about, is semi-permeable in nature. Hard shell of the egg is chemically calcium carbonate, right? So shell is calcium carbonate. Beneath this shell is SPM, and inside the SPM are the contents of egg. Now, if we take two eggs, raw eggs, these are not boiled, we take dilute HCl in two beakers, put these eggs in dilute HCl, slowly reaction between hard shell, that is calcium carbonate, and HCl will take place. Calcium carbonate, that is shell, will dissolve after some time. And after that, what will be exposed? That semi-permeable membrane will be exposed. Now, if we take out this egg without the hard shell now, put one of them in pure water and the other in a concentrated solution of sodium chloride. The one which is put in pure water, it will gradually swell up due to end osmosis. And the other one will gradually shrink due to exosmosis. And this is the question which has been asked many times in exam. Pattern. Next paragraph. Beneath hard shell of an egg is a thin membrane, which is SPM in nature, which is semi-permeable membrane in nature. If an egg whose shell has been dissolved in dilute acid, is placed in pure water, it will swell up due to endosmosis, because water will behave as hypotonic solution. On the other hand, if such an egg is placed in a concentrated solution of sodium chloride, it will shrink due to exosmosis. Now, last topic for today, heading is reverse osmosis. Reverse osmosis. What is the abbreviation? RO. You're using RO at home based on this principle, which I'm going to explain right now. Look here. I explained this experiment. Solvent flows in this direction from outside. It goes inside the thistle funnel. Now, to stop the process of osmosis, I explained we apply some pressure on the solution so that the entry of solvent just stops. For that, how much pressure we apply, that is osmotic pressure. Now listen carefully. if pressure applied on the solution is less than OP, if pressure applied on the solution is less than osmotic pressure, then some water, some solvent will enter. It means osmosis will still take place. But if I apply pressure more than osmotic pressure, then solvent will flow out from the solution. It means if pressure applied is more than osmotic pressure, flow of solvent will take place in the reverse direction than osmosis. And that's what is called reverse osmosis. So for reverse osmosis, we have to apply pressure more than osmotic pressure of the solution so that solvent flows from a concentrated solution towards dilute solution. Pattern. It is the process of flow of solvent from a concentrated solution towards dilute solution through SPM when pressure more than OP is applied on the solution. When pressure more than osmotic pressure is applied on the solution. Its main application is desalination of seawater. All the bookish languages, desalination of seawater. But in general, we can say this is used for desalination of salts present in water. So that's all for today, but look at one diagram and drawing. In board for many, many years, there was a question based on this diagram only. Question used to be identify the process represented by this diagram and what is the main application. This diagram used to be for reverse osmosis. See, diagram used to be like this. Seawater and pure water are separated from each other by semi-permeable membrane. And this is the piston, cylinder fitted with the piston. We apply pressure more than osmotic pressure. Rest is nothing but reverse osmosis. I explained water will flow from seawater into pure water and water will be purified. Right? So this used to be in the form of a diagram. You never know, can be asked. Right, children, in the next class, we'll finish the chapter and after that, we'll start with organic chemistry. I hope you are watching videos on YouTube. In case you're not able to understand a particular topic, please watch my video. Watch assignments are also discussed. I'm fully explaining assignments also and uploading. Although it will take time, but I'm trying everything. Right? Right, children, you can log out.
Thank you, sir.
Bye, sir.
Bye, sir.
Thank you, sir.
Thank you, sir.